So we're going to be talking about sampling distributions for proportions and kind of what they mean. And so one real quick thing here, I want to recap what we saw yesterday with being unbiased. It says when estimating a population parameter, an estimator is unbiased if, on average, the value of the estimator is equal to the population parameter. Again, what that means is when you're looking at the distribution of your samples, they're centered or they're averaged around what you expected the average to be. And so part of that means we do have to make a guess as to what we would expect the parameter to be. We'll see that in a minute. Variability can be modeled using probability. That doesn't really mean anything to us yet. And a sample statistic is a point estimator to the corresponding population parameter. Again, that doesn't mean too much, but it's true. All right, so let's look at this specifically for proportions. Now, essentially what this is saying here, maybe you can pause this and read it. It's saying that the average that we would expect to find of all sample proportions, so the average of each sample proportion altogether should be equal to the population proportion. So this p hat has to do with the sample that we get, and this regular p has to do with the actual proportion of the population. So it's saying the average value you should expect from all samples of a certain size should just be equal to the true value in the population, and the standard deviation of all of your samples should be equal to this formula, which notice again uses the population answer. So in other words, when you look at these questions on Khan Academy, you're looking for the assumed truth in your calculations. So we are going to make an assumption about what the population proportion is, and that assumption, not any particular sample, guides how these values are made up. So it also says if sampling without replacement, the standard deviation is smaller than what's given here, but if we sample less than 10% of the population, the difference is negligible. So in other words, this is kind of what we talked about yesterday. As long as we sample under 10% of our population of interest, all of this is valid. If we sample more than 10%, people have figured out ways to still do valid means and valid standard deviations, but you do have to adjust your formula because you're sampling a larger portion of your population. But we don't worry about that. The other thing to know is that we do want this to be approximately normal, and you can ensure that by having this hold true, which we talked about yesterday. All right, so that being said, I think we're ready to dive into some Khan Academies here. And we'll look at, the mean and standard deviations of sample proportions. I'll make this a little bit bigger for now. All right, so they say they're going to take a simple random sample of 250 from the approximately 15,000 households who subscribe to them. They found that 75% of the sampled households watch sports on television at least once a month. The company is considering taking more samples like this. Suppose it is actually 70% of their total subscribed households who watch sports. So again, there's some misleading going on here because it has to do with this idea right here. Just because you get a certain sample proportion, the mean of your sample proportions is actually what the truth is, the true population proportion. So I say that to say, they talk about, they took a sample and found that 75% watch households on television. That is a particular p hat, but the average of all our p hats should be what the true proportion is. And that's what this whole, suppose it's actually 70% who watch. So that means, write this over here, that the mean that we would expect from all of our sample proportions, I'm sure you found one particular one that came back as 75, but if we were to take many, all possible combinations of 250 of the 15,000 and kind of average them out, it should approach 0.7, because that's what 70% is as a decimal, or as a proportion, because that is what the actual amount is. So again, I'm going to say it one more time, but it still might not make sense yet. This variable, what this denotes is this is saying what you would expect to find after comparing all possible groupings of 250 out of the 15,000, you should get 0.7. Now let's find the standard deviation of this. The standard deviation, if you look back to this, again, uses that true or assumed value and your sample size. So this n doesn't have to do with how many are in the population. This n has to do with how many you sample. And that's again why we said yesterday that you can somewhat control for variability, because standard deviation is a measure of variability, by changing your sample size. You can see if you have a larger n, you're dividing by a larger number, so you're actually decreasing the size of the standard deviation. So that's why larger samples are better, because you can bring your data values closer together. That's not totally what we're asking right now, but it's worth mentioning. So anyways, the standard deviation here is going to be, put the problem back here too. Let's see here, we sampled 250, so the standard deviation is going to be the square root of, again, the true proportion of successes times 1 minus p, so the opposite of 0.7, which is 0.3, divided by our sample size. Because again, sample size can help control variability. So that is, again, the standard deviation of all similar groupings of 250 people out of 15,000. You would expect their standard deviation to be about this much. So, well, I guess I'll just calculate this for now, or we'll choose it. This was tempting, but notice they used the total size, not the sample size. This would be our correct answer. Maybe let's just go through and look at the rest of these. So suppose that 93% of approximately 1,000 total, so again, this is the assumed truth kind of line, are up to date on their stats. They're planning on taking a simple random sample of 40 dogs to see what proportion of dogs are sampled and up to date, and what are the means and standard deviations of that sampling distribution. So again, we're trying to find what do we expect when we sample 40 dogs, what would we expect on average, and how much should it vary? Well, what we would expect on average is just the proportion we would get from 40 dogs. So that would be 40 times, actually no, it wouldn't be 40 times, it would just be the actual proportion. That's a trick question. I saw that answer choice and it made me go towards it. So again, the mean of your sample proportion, let's look back at the formula, is just the population proportion. Sample size has nothing to do with the mean. The mean of your sample proportion is just the total amount, so the 0.93, or the total proportion. Right? Now when we calculate the standard deviation, for all sample sizes of 40, we would expect them to be varied about this much. Well, 0.93 times the opposite, which would be 0.07, all over 40. And let's choose that answer. There we go. All right. Going on again, group of scientists take a simple random sample of 25 to see what proportion have below 0. Suppose that 41% of days in the city have that. So again, they're saying they want to take a sample of 25. Suppose the true value, the true proportion is 41. So then what will we expect our sample proportion distribution to look like? Well, its mean, again, would just be the actual proportion, which was 41%. The standard deviation for that would be the square root of, again, the 41% times the opposite probability, which would be 59%, all over 25, because that's the sample size. Oops. This one. Notice this time they didn't actually calculate the 59, they just wrote it as the opposite of 41. Okay, and last example here. So they don't have that kind of trick question again. Again, it's just going to be 0.75, and notice they're taking a simple random sample of 200 teenagers from the population of teenagers in North America. So 200 is definitely under 10% of all teenagers in North America. So 0.75, and then the standard deviation takes into account the sample size. Okay, so that's the first con assignment. Let's look at the second, which is finding probabilities with these sampling distributions. So in other words, if you can find a mean and standard deviation, can you then find a probability based on that mean and standard deviation for a particular sample? Okay, so it says an article claimed that only 38% of hotel visitors used an alarm clock. Now, in other words, the claim is the assumed truth. So we'll write that down, and we can now figure out our standard deviation as well, which would be 0.38 times the opposite, which would be 0.62 over, well, how many are we going to sample? We're sampling 700, which is under 10% of 10,000. So this is our standard deviation. And then notice here it says, of the sampled visitors, only 35% used an alarm clock. And we get a little bit more clarification here. Assuming the 38% is the true proportion, what is the probability that less than 35 use the alarm clock? Now here's the idea. This is going to be approximately normal for the ideas mentioned right here. So you can kind of figure out that 38% of 700 is definitely more than 10, and the opposite probability, 62% is also of 700, way more than 10. So this distribution is approximately normal, and we want to figure out the odds of getting less than 35. Well, here's what that looks like. Maybe let's calculate what our standard deviation actually is. It's very small. It's 0.0183. And remember that this is normally distributed, so one standard deviation away from either side should be about 68% of the data. 2 standard deviations is 95% of the data. Now it's centered around 0.38, or z-score of 0. And this would be minus 1 standard deviation, so this 1 standard deviation away is going to be about 0.362 something, and this one's going to be 0.398 something. You can kind of see where I'm getting those values, just adding and subtracting 1, just giving you an idea of what the shape of this looks like. And we want to find the odds of being less than 0.35. We want this probability. So we can do that in the calculator, and you can do that using the normal distribution, normal CDF with these values, or you can also go to, let's see here, we can go to stat. Actually, no, we're not ready for that yet. We are going to go back to the normal CDF. And our lower is just going to be that really big negative number. Our upper is the 0.35. Our mean is 0.38. And our standard deviation is, we should be able to use the rounded amount. Should be close enough. So I get 0.0505, and so that means A is the correct answer choice. All right, so maybe I'll just do one more of these because I think this section makes a little more sense. I'm going to skip over some of the reading. So assuming the agency's 30% claim is correct, cool, so now I know 2 pieces of information. I know that the mean of all sample sizes, or all samples of similar sizes, should just come out to 0.3. All the means of all proportions of similar sizes should just come out to the assumed truth. And the standard deviation for all samples of equal sizes should come out to the 0.3 times its opposite, 0.7, over how many we're sampling this time, which is 150 of 8,000. Let's calculate what this is. Square root of 0.3 times 0.7 divided by 150. I get 0.0374. Again, I'm going to draw a distribution to help visualize this. It is approximately normal because, again, 30% of 150 is 45. 70% of 150 is 105. Both of those are greater than 10, so we do have an approximately normal distribution. That approximately normal distribution is centered around 0.3. 1 standard deviation away would be 0.337, blah, blah, blah. 1 standard deviation less would be 0.2626, if you kind of see where I'm calculating that. And again, it goes on and on and on, just trying to give you an idea of what this looks like, how spread apart the data is. And again, what's controlling that spread ultimately is the sample size. If this sample size was 300 of 8,000, this, 1 standard deviation away would be actually a lot closer together. This value would be a lot smaller, just to say that. Anyways, we want to find the odds that more than 36%, more than 36, so that means we're looking about right here, 0.36 and more. So it should be a fairly small amount. We'll go back to normal CDF. And this time our lower is the 0.36. That's our lowest amount. We can go as high as we want, so up to, I don't know, some really big number. Our mean is just 0.3, and our standard deviation is 0.0374. And we get 0.05 again. There we go. All right, so hopefully this is starting to make sense. Ooh. All right, just make sure you're reading this. They say within 2 percentage points of 63%. So you can even see from the answer choices where this comes from. So this just means your lower is 0.61, your upper is 0.65. Your mean is 0.63, and your standard deviation would be the square root of 0.63 times 0.37, all divided by 600 in that square root. That would give you your correct answer.